relations and functions. We are continuing. We have just defined relations. We were going through the type of relations. We have discussed null relation, universal relation, identity relation. Now we go for something new. We start with reflexive relation. When do you say a relation is reflexive? A relation R from A to A is said to be reflexive if AA is a member of R for all A. That means every element must be related to the same element. Of course, it is possible because it is from A to A. If every element is related to the same element, then the relation is called a reflexive relation. Let's take an example. Suppose A is 1, 2, 3. We define a relation from A to A defined by R equal to set of x, y, such that x less than or equal to y. It is a reflexive relation. Why? Because xx is a member of the relation. Why? X is less than or equal to x is true for all x in R, for all x in A. So that means xx is a member of R for all x in A. Here we can list the elements of R: 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. Of course, xx is there because 1, 1 is there, 2, 2 is there, 3, 3 is there. There may be more elements also, but we need minimum 1, 1, 2, 2, and 3, 3. So this is a reflexive relation. Whereas, if we take on the same set A, R from A to A, R equal to set of x, y such that x less than y squared, it is not reflexive because 1, 1 is not there. 1 less than 1 squared is not true. Every other 2, 2, 3, 3 is there, but 1, 1 is not there. 1 less than 1 squared is x less than y squared. It's not true. 1 less than 1 squared is not. And hence 1, 1 is not a member of R. And hence it is not a reflexive relation. We can easily note that every identity relation is very much reflexive, but all reflexive relation need not be identity relation. There may be reflexive relation which are not identity relation. For an example, set let A is equal to 2, 3, 4. R is equal to set of x, y such that x is a factor of y. It is very much reflexive. 2, 2 is there, 3, 3 is there, 4, 4 is there. But this is not the identity relation, because if I list the relation, what will be the relation? It will be 2, 2, 3, 3, 4, 4 and 2, 4 is also there. It is not identity relation, but it is reflexive. So all identity relation are reflexive, but the converse is not. There may be reflexive relations that are not identity relation. R is obviously reflexive, but R is not an identity relation. Next is symmetric relation. The relation R from A to A is said to be symmetric. If AB belongs to R implies BA belongs to R for all A and B. That means whenever A is related to B, then B must be related to A. If so, the relation is called a symmetric relation. Whenever A is related to B, then B is related to A. If A is related to B, then B is also related. It is true. If it is true for all A and B, then it is a symmetric relation. For example, R from n to n, n is a set of natural numbers. N to n, set of x, y such that mod x minus y equal to 2. Well, we can show it is symmetric because how do we show? Suppose xy is a member of R. When xy is a member of R, mod x minus y is equal to 2. But mod x minus y is equal to 2 is as good as mod y minus x equal to 2. That means yx is a member of R. So what we observe is when xy is a member of R, yx is also a member of R. That means the relation is symmetric. But if it takes R from n to n, R equal to set of xy, where x less than or equal to y, it is not symmetric. Because you may have 1 3 member of R because 1 less than or equal to 3, whereas 3 1 is not a member of R. So this relation set of xy such that x less than or equal to y, it is not symmetric. You can easily observe x less than or equal to y is reflexive because xx will be a member of. Okay, we go ahead with next one, transitive relation. A relation R from A to A is said to be transitive if AB belongs to R and BC belongs to R, then AC must be a member of R. Understand it very carefully. This means A is related to B and B is related to C. Remember, A is related to B, A is related to B, and that B, A is related to B, and that B is related to another number C. Then A must be related to C. If it is so, whenever AB and BC, the second element here must be the first element in another one, then this A and C must be related. So whenever AB is a member of R, BC is a member of R, then AC must be a member of R. Then and then only we say the relation is transitive. Take a simple example. A relation from n to n in a set of natural numbers are equal to set of xy such that x the less than y. It is transitive relation. R from n to n are equal to set of xy such that x less than y. R is transitive. Why? Because if AB member of R and BC member of R, that means A less than B and B less than C. AB member of R means A less than B and BC member of R means B less than C. So A less than B and B less than C. Naturally, A is less than C. When A is less than C, that means AC member of R. That is the relation. Whenever X less than Y, XY is a member of R. So AC member of R. So when AB member of R and BC member of R, that implies AC member of R. And hence, R is transitive. So understand very carefully. Transitive relation. When AB is a member of R and BC is a member of R, then AC must be a member. So we discussed three relations. Reflexive, that is whenever every member is related to the same element. Symmetric, that is whenever A is related to B, B must be related to A. And transitive, A is related to B and B is related to C, then A is related to C. Well, seventh is equivalence relation. A relation R from A to A is called an equivalence relation if it is reflexive, symmetric, and transitive. Very important. Started with reflexive relation, then we had symmetric relation, we had transitive relation. When a relation is reflexive, symmetric, as well as transitive, it is called an equivalence relation. So if you want to prove a relation is an equivalence relation, we have to prove all three. It's reflexive, symmetric, and transitive. Let's take an example. Show that a relation R from n to n defined as R equal to set of xy such that mod x minus y is a multiple of 4 is an equivalence relation. Can easily show it is reflexive because mod x minus x equal to 0. 0 is very much multiple of 4. That means xx is a member of R or is reflexive. So mod x minus x equal to 0. 0 is a multiple of 4. This is true for all x. That means xx is a member of R for all x in n. Therefore, R is symmetric. R is reflexive. Now for symmetry, xy member of R implies, I think this is as good as earlier one. Xy member of R implies mod x minus y is a multiple of 4. Naturally, that is as good as mod y minus x is a multiple of 4. Mod x minus y and mod y minus x is the same. So whenever xy is a member of R, yx also a member of R. Hence the relation is symmetric. R is transitive also. Why? Because xy member of R and yz member of R implies mod x minus y is a multiple of 4 and mod y minus z is a multiple. How will you show mod x minus z is a multiple of 4? We cannot add two modulus and we get another modulus. That is not true. So what we do is that, let us proceed. Mod x minus y is a multiple of 4 means x minus y is a multiple of 4. This may be positive or negative. Whenever mod x minus y is a multiple of 4, x minus y is also a multiple of 4. And whenever mod y minus z is a multiple of 4, y minus z is also a multiple of 4. That multiple may be positive or negative. That is why take your mn belongs to z. Not necessarily mn in all natural numbers here. Mn may be any integer. When x minus y and y minus z both are multiple of 4, we add this. So x minus z will be x minus y plus y minus z, which is 4m plus 4n, that is 4 into m plus n, which is a multiple of 4. So x minus z is a multiple of 4, which shows that mod x minus z is a multiple of 4. Mod x minus z is a multiple of 4, which shows that xz is also a member. Once again, if xy is a member of R and y is a member of R, mod x minus y is a multiple of 4, mod y minus z is a multiple of 4. Mod x minus y multiple of 4 means x minus y is also 4 into m, where m is not necessarily natural number, m is an integer. And y minus z is also multiple of 4. Add up these two, you get x minus z, you can write x minus y plus y minus z. That is 4m plus 4n, that is 4 into m plus n. Again a multiple of 4. So mod x minus z is a multiple of 4. That means xz is a member of R. That means from 1 to 1, 3. 1 we have shown it is reflexive, 2 we have shown it is symmetric, and 3 we are showing it is transitive, and hence R is an equivalence relation. Well, let us note that if you want to show a relation is not reflexive, if you want to show it is reflexive, we have to show it is true for all A. But if you want to show it is not reflexive, we produce at least one example for a counter proof. We only want a counter example, or if you want to disprove something, you only want an example. But proving cannot be done by example. So if you want to show R is not reflexive, we produce at least one example. What will do for us? One example of AA, where AA is not a member of R, or A is not related to R. Whereas if you want to show it is reflexive, we have to show that AA member of R for all A. Similarly, if you want to show R is not symmetric, we produce at least one example of AB member of R where BA is not a member. One example will do. Whereas if you want to show R is symmetric, we have to show that AB member of R implies BA member of R. Similarly, if you want to show R is not transitive, be very careful here. To show it is not transitive, we produce two pairs AB and BC, both of which are elements of R, where AC is not a member of R. Whereas to show that R is transitive, we have to show that AB member of R and BC member of R implies AC member of R, as we have done earlier. Remember something more important here. Or we can claim that it is transitive by this. If AB member of R, then AB member of R means if A is related to B, then B cannot be related to any other member. Or if AB member of R, then B cannot be the first component of any element of R. If you can show that, then the transitivity is not violated. Remember, when the transitivity is not violated, it is transitive. It is not transitive only when the transitivity is violated. That is what I have written here. If we cannot produce any set of ordered pairs AB and BC, both of them are members of R, then R is not at all violating the transitive condition, and hence R is transitive. It is not transitive only if it violates transitivity condition. If you claim that it doesn't violate the transitivity condition, we have to claim, or we have to assure it is transitive. I'm taking up a few examples here. Let A be the set of people in a town. find which of these relations are transitive. One is R1. I'm calling it R1. From A to A, we defined as R1 equal to set of XY, where X is a brother of Y. We have to find out whether it is transitive or not. Let us take another one is R2 from A to A. What is A here? A is set of people in a town. R2 from A to A is R2, set of XY, where X is wife of Y. R3 from A to A. R3 is set of XY, where X is the son of Y. Let us look 3. Take care of remembering these three relations. R1 from A to A. All are from A to A. R1 is set of XY, where X is a brother of Y. R2 is set of XY, such that X is a wife of Y. R3 is set from A to A, where R3 is set of XY, where X is the son of Y. Let's take the first one. R1 from A to A, R1 equal to set of XY, where X is a brother of Y. That is, let us suppose XY member of R1 and YZ member of R1. That means X is a brother of Y and Y is a brother of Z. Can you not say that X is a brother of Z? Are you hearing?
Yes, sir.
Yes, X is a brother of Y, Y is a brother of Z. Naturally, X is a brother of Z. So X,
But
Y,
sir, cousin.
R1, X, Z is a member of R1. R1 is transitive. Now one more question to Is it reflexive? Sorry, is it symmetric? I mean, my question to is it symmetric? XY member of R, X is a brother of Y. Hello?
Yes, sir.
Is it symmetric? X is a brother of Y. Can you not say Y is a brother of X?
Yes, sir.
Why not? Y could be a sister of X. No.
Oh,
It's not symmetric. X is a brother of Y. But Y may be sister of X. It is not symmetric. Be careful. Let's understand very carefully. Now let's
yes,
take the
sir.
second one. A is a set of people in a town. R2 from A to A. R2 equal to set of XY, where X is wife of Y. Is it transitive? Manav?
Yes,
Hello?
sir.
Is it transitive? X is a wife of Y. XY is a member of R. X is a wife of Y. Can you just tell? Is it transitive? Well, let us see. XY member of R2, that is X is the wife of Y. Well, what is transitivity? If XY member of R and YZ member of R, then X should be member of R. Okay, XY member of R2. Now I want YZ member of R2. Come on, is it possible? We must get Y is a wife of Z. Oh, how is it possible?
No, sir.
Here, X is a
Yes, sir.
wife
X
of
is
Y.
yes, sir.
X is a lady and Y is a gentleman. X is a wife of Y. How can Y be wife of someone else? X is a lady and Y is a gentleman. That means XY is a member of the relation. X is a wife of Y. You cannot find another YZ. When XY is a member of R2 and you cannot find YZ. What does that mean? It's not possible, which cannot happen. That means, what do you conclude? What do you conclude? Is it transitive or not?
No, sir.
There you lost. Because what is it violating transitivity condition? It is violating only when XY member of R2 and YZ member of R2 and XZ not member of R2. But here, the precondition is not satisfying, means it is not violating. We'll go back. We have discussed it earlier. If you remember it. back here. Yes, if we cannot produce any A, B, and BC, then the transitivity conditions are not violated. R is not violating the transitivity condition, and we have to say R is transitive. What are the transitivity require? If you produce A, B, and BC, then only you can look for AC. If you fail to produce A, B, and BC, then it is still transitive. Understand it very carefully. This is a good example for understanding. That is why I taken up this, right? X a brother of Y, that is transitive for the wife of Y. X is the wife of Y. Look very carefully. When XY member of R2, X a wife of Y. Now to have YZ member of R2, we must get Y is the wife of Y, which cannot happen. Which cannot happen. That means the transitivity condition is not violated here at all. Understand very carefully. You will not produce X, Y, and YZ. Only when you produce X, Y, and YZ, then only you have to guarantee XZ for being transitive. If you do not produce X, Y, and YZ, that is still being transitive. Only when it is violating a transitivity condition, it's not transitive. So hence you have to conclude that this relation is very much transitive. Be careful. It's a very good understandable question. When you fail to produce X, Y, YZ, any case, it is true that when X is a member related to Y, Y cannot be related to any other member. So the transitivity is not violated anywhere, hence it is transitive. What about the other one? That is simple. X is a son of Y. XY member of R3, YZ member of R3. It is quite simple. It is possible. X is a son of Y and Y is a son of Z. And in fact, X is not son of Z. X will be grandson. That means X is not son of Z. Obviously, it is not trans. XZ is not a member of R3 and R3 is not. So clear about what is reflexivity, symmetry, and transitivity. We have taken a few examples. Now I'm giving you two questions. One, show that the relation R from N to N is set of natural numbers, R equal to set of AB where A raised to B equal to B raised to A is an equivalence relation. You have to show it is reflexive, you have to show it is symmetric, and you have to show it is transitive. Be ready with the answers. I will ask tomorrow. Third one, A is equal to 2, 3, 4, 5, dot, dot, dot. That means set of all natural numbers excepting 1. I did not include 1 here. Verify whether the following relations defined are reflexive, symmetric, or transitive. First one is R equal to set of XY where X and Y have a common factor other than 1. And second is another relation. I am using the same notation, no problem. Set of XY where X and Y have no common factors other than. Well, XY, first one, they have common factors other than 1. Here are no common factors other than. Okay, go for it. Have a nice day. We'll meet back tomorrow.